Alright, so now that you've had a little bit of time to think about how to do half reactions, the half reaction method for balancing redox reactions, now we're going to take a look at a couple more meaty kinds of problems. Problems that are a little bit more realistic than the simple ionic one that I gave you in that first kind of half of the video. So let's take a look at this. A lot of the reactions that we're going to work with have things that seem to appear and disappear. Like, for example, this little ionic equation I have on here, which is permanganate ion plus iodide ion to produce iodine gas and manganese ion. Where's the oxygen go? This is pretty common when you're presented with these initial ionic equations, that you'll have hydrogens and oxygens that sort of appear or disappear. And this is because the redox reactions that we're dealing with oftentimes occur in acidic solutions. Our book only deals with acidic solutions, but you need to be aware that basic solutions are also possible. But like I said, our book deals only with acidic, so that's only what we're going to deal with in this particular case. But for example, your battery in your car or in your any of your iPods or anything along those lines, there's a little bit of acid in there that helps to provide that sort of reaction energy to move along. So in terms of doing redox reactions with these, it's a lot like what we talked about before. It's on the same basic principles, but there's some additional stuff that we have to be able to do to deal with those hydrogens and oxygens that come along with it. So let's take a look at this example. So for example, moving along, I'm going to use the same example, this permanganate equation, that I'm going to talk about this one as our kind of our basic skeleton equation we're going to use throughout. We start off in kind of a similar way. Number one, we've got to assign oxidation numbers to everything. And then you have to write the half reaction. So again, you have to write the iodine equation and then the manganese equation. Again, in this case, oxygen's around, but it's not really participating in the redox in terms of what's going on in here. So again, you got to take a look, apply all of your oxidation level or oxidation rules to figure out what they are. You should get that manganese here as a 7+, kind of a weird one. You'll see this one a lot, so we'll get to use that one quite a bit. But then you got to take a look at how all the elements balance. There's a second little rule here, which is balance elements other than hydrogen and oxygen. We didn't have this in the first example, but here there's a little bit of a difference. We've got one iodine on the left, and we've got iodine 2, it's diatomic, on the right. So I had to balance that first, and that's one of the first things that we have to do with some of these, is just to check to make sure that other than hydrogen and oxygen, our elements balanced. Our manganese was fine because there's only one on each side, but that iodine, especially with the diatomic gases, is where this one comes up. You got to put a 2 on the other side. Okay, moving along. Now, we have to take care of those hydrogen and oxygens. And this is kind of the weird part. Keep in mind that these reactions are occurring in solution. So number one, there's water present that we can use. That's our oxygen source. Number two, keep in mind that these are all happening in acidic solutions like our batteries, and that's our hydrogen ion source. So these two things, even though they don't appear in that initial equation, they're there for us to be able to use to balance this equation, and they do participate. They don't just hang around on the outside. They jump right in there and help this reaction to occur. So our first little half reaction, the iodine half reaction, is fine. It doesn't have hydrogen or oxygen present. So that was the carryover from the last screen. But down here, we had to do a couple of different things. So I did the blue step first, and I did the green step second. So I took a look at this and went, all right, I've got oxygen present over here, so I'm going to need oxygen present on the right side. And the way I balanced that was by adding 4 oxygens. Those oxygens come in the form of water, so I added 4 water molecules, and there they are. Now that I've got that side done, I kind of seesaw back over to the other side. Now that I've added these hydrogens, I have to take care of the hydrogens on the left. So I added 4 water molecules. That gives us 8 hydrogens because it's 4H2. So that means on my other side I balance out those hydrogens that I just added by adding 8 hydrogen ions. So in other words, for this reaction to occur, it's kind of using 8 hydrogen ions from the environment, from that acidic environment, and it's going to produce 4 water molecules to go back into that aqueous environment. So again, it's kind of you do the oxygens on one side and then hydrogens on the other side, or it could be vice versa, I suppose. But this is the weird step, the big difference between the other ones, and this one comes up very commonly, so pay attention to this one. All right, now that we've got that part done, now we need to take a look at that electron side. This is similar to what we did before. We have to take a look at how many electrons are gained and lost, but there's a couple of tweaks now as we've kind of moved into this more advanced level. So number one, we take a look at our iodine equation. Iodine went from -1 to 0, so 1 electron was transferred. However, because there are 2 iodine atoms present, our total number of electrons that's being transferred here is 2. So that's a little bit of a trick. So what's the total electrons? 1 per iodine, but there's 2 iodines, so 2 electrons total. Second thing, Now we want to take a look at, in the second part, how many electrons are transferred here. This blue statement is kind of the key bit. Make sure that when you're balancing your electrons, you're only looking at the element that's being oxidized or reduced. In this case, that's the manganese. We're really focusing on what's happening to the manganese. And in this case, 5 electrons have been transferred. It's going from a 7 to a 2. So I had to put the 5 electrons on the high side again, so I added the 5 electrons over on this side. And again, just as a reminder from the last one, if you've done this right, you should have electrons going in on one equation and then out on the other equation. Doesn't matter which one's top or bottom, but as long as you've got those electrons coming in on the opposite sides. Okay, next step, just like the previous ones, we've got to use those coefficients again to balance the electrons gained and lost. So this is one of those cases where both of our equations have to have coefficients in front of them, because I've got 2 electrons lost and I've got 5 electrons gained. Our lowest common denominator between a 5 and a 2 is 10, so that's why I multiplied this top equation by 5. And I multiplied this bottom equation by 2. Again, this is just balancing the electrons in, electrons out. And again, I mentioned this in the last video, but that's okay to have multipliers in both equations. Especially it seems like these equations have manganate in them, MnO4. This seems to happen a lot because of this 5 electron transfer. Just one of those little weird things. Okay, now just like we did previously, we have to combine our 2 half reactions. I've distributed and combined kind of on the same screen here. So here's me distributing my 5 across the top. So I get 10 iodine ions, 5 iodine gas molecules, and 10 electrons. And then in my bottom one, I distributed my, I guess it was a 5 across there. No, I distributed my 2 across there. So now I have 10 electrons, I have 16 hydrogens, 2 manganates. I put the parentheses around here just to sort of make it easier for you guys to see that it's 2 manganate and this negative sign goes along with that whole thing. It seemed to get lost if I didn't do that, so that's why those parentheses are there. We've got 2 manganese ions and then 8 water molecules. So again, I distributed. Now when I combine them, I get this monstrously long equation down at the bottom. Again, all the species on the left go on the left side of the arrow, all the species on the right go on the right side of the arrow, and don't get lazy. It's really critical to make sure that you carry down charges. So things like this is an iodine ion and this is a manganese ion. That's really important to do that. It's something I will be looking for, and I will certainly take off points if you don't do that. So again, don't get lazy. Carry those charges down. Next step, as we did before, we cancel out identical species. In this particular case, the only identical species we have is electrons. And that's a good thing. We should have electrons the same on both sides. That's one of the ways our equation has to balance. Electrons in equals electrons out. Nothing else exactly balances. Yes, we have 10 iodine here, and we have 10 iodine here, but they're not exactly the same species, so we can't cancel them out. This is iodide, ions, and this is iodine gas, so we're not allowed to cancel those out. So the rest of it's all going to stay there. And then the last thing we do is we check for balance. So now, again, you got to check for balance in a couple of different ways. You got to check for charge balance, and then you have to check for element count balance. When you're doing charges, it's critical here at this point in time that you only use charges and not oxidation numbers. So for example, see I didn't put that 7 plus in there and I didn't put that 2 minus in there. Same thing over here in the hydrogen and the water. I didn't put the 1 plus and the 2 minus over there. These are molecules, or this whole thing is an ion. So I want to look at that whole thing as a group. It'll actually work out if you do it right the other way, but it's kind of a pain in the butt. So trust me on this one, okay? So when I look at my total charges, I've got 16 positive charges from these hydrogen ions. I have 2 negative charges because I have 2 manganate ions present, and I have 10 negative charges from my iodide ions that are present. That gives me a total net charge of 4 plus on the left. And then over here on the right, I've got 2 manganese ions, so that gives me 4 plus. Water is a molecule, so it's got a charge of 0, and iodine is a molecule, so it also has a charge of 0. So I have a total of a 4 plus on the right. So therefore it's balanced. 4 plus on the left, 4 plus on the right. So that worked out pretty good. Last thing, you got to check to make sure that your element counts are the same on both sides. And I've got 16 hydrogens on both sides, 2 manganese on both sides, 8 oxygens. Remember this 2 distributes across. It's a little bit of a weird one. And then 10 iodine atoms on each side. So in this case, when I'm just checking for element counts, they don't have to be the exact same species. I'm just looking for kinds of atoms. So the charges for the element count doesn't make a difference. So there you go. That lets me think that my whole thing is definitely ready to go. I've left you here one kind of a beast of a problem as well as a practice problem. You're going to want to hit pause on this one and see if you can work this one out. These are really challenging. I understand that, so you might want to have your notes out next to you so that you can take a look at that, because this process of going back and forth is kind of challenging. So the one that I've got for you here is a cerium atom. 4 plus to 3 plus, and this is arsenic acid. How's that for a crazy name? H3ASO3 and arsenous acid, H3ASO4. So it's kind of transferring between the two of them. Here's a short list of steps, kind of hints. Hit pause while you've got these steps up here, and then I'm going to move on to the next slide so that I can go through the answer with you. I'm not going to go through step by step, bring it to class, but I'll go through at least what the final answer is. Okay, hit pause. There we go. So here is our solution. Here's my two half reactions, and they have been balanced. In red here, you can see that I've put down all of the oxidation numbers. All the other oxidation numbers are charges, so they kind of show pretty easily. This hydrogen here is a 1 plus, and oxygen is a 2 minus, like it always is. But there you can see that. Common mistake is for students to get the oxidation numbers wrong. If you get the oxidation numbers wrong, the whole rest of the problem is going to be wrong because your electrons transferred is going to be wrong as well. So that can be kind of a mess. We had 2 electrons lost, so I had to make this 2 electrons gained. I had to add a couple of, let's see, what did I start with? There was 3 oxygens here and 4 oxygens here. That's why I had to add a water molecule, and then I added the hydrogen molecules to balance them out. And then here is our final combined reaction. So it's all balanced out. Hopefully that worked for you. If not, kind of look at it closely, bring it into class, and we can go through it step by step. I know these are challenging, but you can do them. It just takes some patience and some practice to get the steps right. So there you go. There's your big ideas for how to do these things. When you're doing redox reactions, you have to balance atoms, charge, and electrons transferred. All 3 of those have to work. When you're doing your half reaction method, when we're going to do the ones in acidic solution, sometimes you're going to get balanced equations that aren't what we would necessarily predict from a regular balanced equation. Extra hydrogens, extra waters, extra oxygens, things like that showing up. It's not necessarily what you'd expect. Because they're occurring in those acidic solutions, you've got hydrogen ions and water molecules to balance out your hydrogen and oxygen. And then for a 4, if you would like to go on, if you're for some reason enjoying this crazy ways, you can take a look at how would balancing redox equations be a little bit different if we were to do it in basic solutions, another way to do it. Or you can take a look at maybe some specific examples of important redox reactions that are done in acidic solutions. So there you go. I hope that made some sense to you. It does take a little bit of practice, so I'll see you in class tomorrow.